Okay. Okay. Well, now is the time to introduce the last speaker of the day. And for me, it's an honor to introduce you Jacques Huyghe, who is the chair in the Bernal Institute of the Biomedical Engineering Program at the University of Limerick in Ireland. His research is focused on poromechanics of swelling materials. So for all people that is working in IVD modeling and cartilage modeling, so as a matter of fact, all our research is based on his contribute, so we are really happy to have you here. And also he is a founder of the International Society of Porous Media that actually focus on the use of all these poromechanics, let's say, tools, not only in the bio field, also in different areas on the industry and engineering. So welcome, Jacques, and thank you very much for being here, and the audience is all yours.
Thank you very much for the nice introduction. It's a pleasure for me to be present here on this convention and this interesting number of people studying the numerical applications of numerical methods in clinical applications and biomedical applications. What I am going to do is a little bit different maybe than what some other people have been presenting here, is that I will go into how to improve the tools that we use in biomedical engineering for numerical simulation so that we can increase the reliability of these tools. To give a little bit of an idea where I am, I have a secondary position in Holland, but my main position is in Ireland and is part of the Bernal Institute. And the Bernal Institute is an institute mostly privately funded from donations and from industry, focusing... Oh, my thing is gone. What happens? Was a problem with Microsoft PowerPoint. That's not good. What's happening now? PowerPoint.
C'est ton PowerPoint qui est sorti?
Disappeared. No, not new present. Open. Open recent. Barcelona. You have it coming back? Si no.
Est-ce que sinon no te vas a presentar?
És que s'havia tancat el PowerPoint.
Però de tota manera ho ha de deixar en mirror, perquè ho té com a segona pantalla. Igual seria més fàcil. Bueno, però aquí té les notes.
On va le mettre un peu plus haut.
Let's see if it remains stable. So Bernal Institute is a project of about 100 million euro, which aims at employing about 400 researchers, mostly funded from donations and from industry, but also a little bit from the government. And there are about 6 or 7 chairs there, one of them being biomedical engineering. And a significant part of the research relates to pharmaceutical science, but is in fact much broader than this, including material science, molecular biology, and energy technology. Now, as far as what I am doing in the Institute, I'm focusing basically on 2 areas. One is intervertebral disc research, and the other one is cardiac mechanics. And both of them are focused on having numerical simulation tools in relationship to experimental setups in the lab. And for the intervertebral disc, we cooperate a lot with Christine Lemaitre from Sheffield and Theo Smith from University of Amsterdam. The themes that we are researching involves voltage-gated ion channels, piezoelectricity, scoliosis, and finite element analysis of electromechanical coupling in the disk. Apart from that, we have a significant line of research in cardiac mechanics, in which we try to fill a serious gap into cardiac mechanics in the sense that we are including coronary perfusion and trying to make a tool which can be used, maybe not for patient-specific problems, but at least to evaluation of cardiac devices. Now, if we look at what happens when we start on finite element analysis of specific organs, such as the intervertebral disc, my experience, and usually that is not very much reported in the literature, my experience is that quite often, because of the complexity of what we are studying, including the fact of heterogeneity of the domain, the anisotropy, very large deformations, discontinuities like contact or fracture, quite often people using standard tools such as abacus or ANSYS or whatever, they get convergence issues. In fact, when we talk with the abacus people of what we are doing, they think, oh, that's never going to work. So obviously, there are publications, nice publications showing, oh yes, 3D analysis, and we took ligaments and contact and fracture, etc. And all of this seems to work. But the reality is that the student has been trying and trying and trying and finally found something which works and then publishes it. And doesn't mention that he checks so many times to actually find something which actually converges. So I think if we want to move towards clinical application of finite element analysis, it should be absolutely reliable and stable. And even in very challenging areas, such as large deformations, strong heterogeneities where the material properties changes orders of magnitude, such as between bone and cartilage. And all of these should not be an obstacle to actually have it running. And so I'm going to talk about what we've been trying to do to improve the situation as it is today. And in trying to do that, we realize that developing finite elements rather than using existing finite elements, when we try to develop finite elements, we have to think across disciplines. We cannot afford to say, oh, we are going to develop specifically for intervertebral disc degeneration a special software which is completely geared to that particular application. It doesn't work because you don't get funding for this. And immediately they expect you clinical applications, some development of a device or something, and you can't get it funded only on that application. But the reality is that when you think of finite element development, this can have a very broad application. And you'll see that I will discuss not only disk, but also application to gels, and gels in particularly in relationship to diapers, nappies, and also in terms of geomechanics, there is the equivalent of herniation of a disc, but then known in geomechanics as hydraulic fracturing. All of these different fields, they need to talk with one another to create the finite elements which are reliable and can be used systematically without worrying about the convergence of the equations. So I'm going to touch on this. I'm going to touch on fracture as well. And I'm talking a little bit about perfusion modeling, where we use similar methods which we are used to have in swelling media. So if we think about swelling media, you can draw many applications, many different applications in terms of the stiffness of the material and in terms of its swelling propensity. And then you see, for instance, sandstone is something very stiff and not swelling at all. If you go down to gels, then you have PVA, which is somewhat swelling, but not so much. HEMA may be a little bit more, and you may have ionized gels, which are much more up in the corner there, but cartilage and disc are somewhat swelling and in the order of megapascal stiffness. But if you talk about intracellular space, you're up to kilopascal stiffness and very high swelling propensity. And especially in that corner, upper right corner there, we get really into trouble. Why? Because the high swelling and high deformability makes the models and the materials extremely versatile and even sometimes unstable. Now, in this area, it's not a small area because most of biology happens intracellularly in cytoskeletons and nuclei, cytoplasm. In those areas, you're down to kilopascal stiffness. And then what you find is that abacus doesn't work. That's the issue. So what to do? And actually 90% of biology takes place intracellularly. So getting funding for intracellular modeling of poromechanics, forget about it. What you can do is use applications from the industry. And now a very famous application, which we all know, is diapers. Diapers are highly swelling. A very efficient product, which all of you who have had children had used a lot. And if you go down to what happens inside the diaper, you find small beads of hydrogel, which swell about 30% of their volume, 30 times their own volume. And they're actually surrounded by some kind of a cross-linked layer on the outside, and you see as it is swelling, and this is actually a bead of this type inside the diaper, when it is faced with a gush of urine, it starts swelling, but before swelling, it has to get this surface shell to crack. And it cracks into pieces, and you see it, oh no. What happened now? It doesn't seem to like it. Recent, we start again. So that's another example. Oh, we can't see it. Wait a minute. I go in presentation mode. That's the issue to get it done. Now, this is also a small bead of such a diaper, and the small bead is looked upon by a very simple method. You know, many optical methods, you use very advanced optics, etc. Here we did nothing of very advanced optics. We took the camera of a mobile phone, you know. You take off even the lens, you do away from the lens, do away with the lens, and you put the bead straight on the chip. On the chip, the CMOS chips, which observes the photos that you take every day with your mobile phone, and you put it on there, and then you look directly on the particle as it is lying on the chip. And so, I hope this is going to work. That's it. Okay, it's almost running away, but you can see very clearly that it has what is called the cauliflower effect. So it swells one side and then the other side, and so it's a very non-homogeneous swelling of the phenomenon. So you see surface instabilities coming up, and to illustrate this even a little bit better, I can show you another video which we've been making of a gel of a cylindrical form, and we move it from high salt concentration to low salt concentration, and then it starts swelling. And it starts swelling, but it develops surface instability, which here you can see very clearly because it starts with a cylinder. And what happens, in fact, is that the outside swells first and the inside doesn't, because the water cannot reach inside. And then the kernel and the outer surface needs to remain in contact with one another. And the way it does, it goes into surface instability and later into a kind of saddle shape. So it is convex to upwards in this plane, and in the plane perpendicular to the picture, it is convex downwards. And so we have a kind of saddle shape, and progressively it is swelling. In the meanwhile, the ions go out of the gel and the water goes inside, and they compete actually with one another. And at some point it goes also into the center of our gel, and progressively then it goes back into the original cylindrical shape. And going back to the cylindrical shape demonstrates that our gel is purely homogeneous. So we have a purely homogeneous gel, but still it goes into those mad shapes. And one of the challenges that we took, and particularly in perspective of what is happening inside the diaper, we actually wanted to be able to simulate this. And I must agree that still now we didn't succeed in simulating what is happening here. But we got some way. And now, because of the special relevance to biology, considering that 90% of biology happens intracellularly, and we pay attention to this also from the point of view of biological application. Now, if we look back in time, you know, I'm working at the Bernal Institute, and Bernal was actually the student from a Nobel Prize winner and also the teacher of 2 Nobel Prize winners. And he worked on proteins. He was the one person in the world who has been the first to apply crystallography to proteins. And one of the most important things that he concluded is that if you want to analyze the structure of a protein, you need to study it in water, because interaction of protein with water is absolutely essential for the structure of the protein themselves, and to understanding the protein themselves. So what we use, basically, practically speaking, in order to study these gels and intervertebral disc is theory of finite deformation of porous solids. And it's actually a very old theory because it dates back to 1972. And on top of that, we use the insights from Flory, also some Nobel Prize winner on swelling, which who argued that you need 3 free energies. One is elastic free energy, the second is mixing free energy, and 3 is the ionic free energy. Ionic free energy is the one which was responsible for Donan osmosis. Many of people working in cartilage and disc know they work with Donan osmosis. So this free energy of ions is very, very important. Mixing energy is in disc and cartilage is known under the name of exclusion phenomenon, and is about responsible for 10% of the swelling in cartilage and disc. Elastic free energy is just the LCST, so that's quite obvious. Now, in terms of gels, Mixing becomes very important when the gel is dry, and increasingly the ionic part may become important if it is an ionic gel, and as swelling goes on, the ionic part becomes more and more important. So we have basically a double layer around every protein or every polymer, and negative charges with compensating positive charges in the fluid, and this is basically what generates most of the ionic swelling, namely around the positive charges there are a lot of water molecules around it. And we can talk about the bi-length, namely the thickness of that double layer, which becomes more as the outer salt concentration becomes less, and less if the outer salt concentration becomes more. Now in gels, unlike disc, you can say that ion diffusion coefficient is typically much larger than pressure diffusion coefficient. Why? Because pressure diffusion coefficient is linked to the stiffness, and because the stiffness is so low, you get low pressure diffusion coefficient, much lower than the ion diffusion coefficient. This relationship does not hold for cartilage and disc. So when we can say this, the nice thing about it is that we can say that the ions go immediately in equilibrium, and we can forget about all of ion diffusion altogether, and we can only focus on this pressure diffusion, what we exactly going to do, and this leaves us with only a fluid and a solid. And then there are equations, and for those people who are at home with equations, this is momentum balance, this is mass balance, and this is Darcy equation. Flow times permeability is equals to permeability times gradient of chemical potential. And we can write these equations down, and we can try to solve them. And the swelling we account for by means of an ionic component, a mixing component, and an elastic component. And I want to go into the details of these equations. But what you do, if you put it into Abacus or any other standard software, you see that everything goes fine as long as you're around megapascal. Megapascal, it's okay, you manage because it converges. But as you go down, and typically this happens inside cells, is that 55 kilopascal, you have most are already failed, and 15 kilopascal, you get no answer at all. So you get really into trouble down to that level, and not only you get into trouble when you go to low stiffnesses, but you get also trouble when you go into heterogeneous materials. You get into trouble when you have strong anisotropy. Many issues are created as soon as you get out of the standard range of application. Now, the question is, why is that so? And can we do something about it? Now, the trouble is that you cannot do something about it inside Abacus or inside ANSYS or whatever package, because you have to be able to look inside. And so what we did, we first analyzed very carefully why the problem comes up. And what we found actually is that one of the key issues here is what is called local violation of mass balance. Local violation of mass balance. Just a very simple experiment. Many of you who have been working on cartilage will know, is consolidation experiment. Consolidation, confined compression. We have a sample of whatever cartilage or whatever lying on a filter. We put a piston on it and we push out water. And as we push out water, we get a settling of the cartilage because water is pushed into the filter. And we can also try to simulate this. Then we have a finite element mesh, a few elements one on top of the other, and we define pressure. And typically we would assume pressure to be linear inside an element. So we have piecewise linear variation of pressure, and then we derive our flow with Darcy's equation, flux equals gradient in pressure times permeability. and then we get a flow for one element, another flow for second element, another flow for third element. Now you see immediately what is the problem is that this element pushes out so much fluid, according to that red line, into the next element, and the next element only less comes in. And same thing with a jump here across the elements, you have a discontinuity. So the flux out of one element is not equal to the next one. And this is not an issue. As long as it is globally accounted for, most of finite elements you can use abacus without any trouble. But when you go to very large deformations, you get really into trouble. And so what we do is basically using a trick which is not new at all. It has been used for years in fluid mechanics. It's the use of what is called Raviart-Thomas elements. Raviart-Thomas elements described in very difficult mathematics books on finite element analysis. And the simplest one which you can think of, which accounts for local mass balance, forces a local mass balance to be true, is one of this type. You have, in 2D, you simply have a square element with on the corners unknown displacement, and you account for the flux through each of the sides, edges, as degrees of freedom on top of the displacement. So where here we are using pressure, here we are using the fluxes across the edges. And we are going to use that element because this one, we'll be able to force the fluxes from one element into the other element to be same, exactly same. And that's what we do. And we force these two fluxes to be exactly same. And the way we proceed is as follows. If you take now the example of a triangular element, you have the displacements unknown in the corners and three fluxes. And on the top of that, we have one pressure, or in case of swelling, it is a chemical potential in the middle. And we can write down the full equations as we have them from the equations I just showed you. Conservation of momentum, conservation of mass, and Darcy's law. And we can solve those equations, but as you see, we have more degrees of freedom than if we had taken pressure simply, because we have those fluxes. And what we do now is enforce these fluxes coming out of one element to be exactly equal to the flux into the other element. So we have two elements next to each other in a big mesh, and so we are forcing this Q3 to be equal to Q3 star by being of a Lagrange multiplier. And what we find is that we can add this condition to our set of equations. And then it becomes a really big equation set with Lagrange multipliers and chemical potential and flux and displacement. And this one will be able to enforce local mass balance. But now we do a further trick, and that's what is called hybridization, where you eliminate the mu and the delta element by element, the Q and the mu element by element, and what you're left with is displacement and these Lagrange multipliers. Now, what are the Lagrange multipliers? They are along that those edges. They are basically the pressure in normal porosity or chemical potential if you include the swelling. So we use this formulation, and we are going to look at a small piece of gel and allow it to swell. And you see, this is what happens. We have tetrahedral elements in 3D, and it can swell to multiple times its own volume, and we get very stable results. And other example, which is maybe even more illustrative, it is a ring fixed to a fixed surface, brought to swell, and it goes into surface instability. That's basically what I showed you experimentally. You can go into significant surface instability and very large deformations because of this creasing going on. And I can assure you, you will never get this kind of calculation done with abacus. But it is typically what happens if you are down to very low stiffnesses, you get surface instabilities. And this kind of analysis is the one which is happening. And you can actually verify also experimentally that the phenomena that you calculate correspond to what you measure. You can plot one relative to the other, the swelling propensity and the stiffness, and then you get one side of the curve where there is surface instability and the other side where there is no surface instability. And same thing with numerical result, stiffness versus swelling, and one side is unstable and the other one is not. So, and now we can go back to our simulation, look at what happens when we take down the stiffness down to 15 kilopascal, and you see that most of our simulations nicely converge. And so this is what we want. We want an absolutely reliable finite element analysis which can be used routinely without each time getting responses, oh, this calculation doesn't work. So going back to the cylinder that I showed you in the beginning of the presentation, we can show that as we take it to lower salt concentration, we get swelling, but also surface instability. You see very clearly the surface instability. It's not at all in the order of magnitude that we had experimentally, but still there is surface instability, and we are working on getting this even more pronounced at what it is here now. So what happens during that swelling is, in fact, underneath the surface, you have a strong compression building up. Compression, here you have surface effective stress. It goes strongly into the negative before rising up again. And this strongly going into the negative is the source of the surface instability that takes place. Now, things are kind of complicated also in terms of material properties. Material properties, we've done experiments, detailed experiments on this, and MIT has also done experiments on this in cartilage, is that if you disallow cartilage to swell and change the salt concentration within which it resides, you will find that the cartilage is going to stiffen as the salt concentration goes down. So we usually think of, material properties, oh, they depend on strain. Stiffness is more on higher strain than lower strain. Now, even if you keep the salt concentration, and you keep the deformation absolutely constant, but this time you change the outside salt concentration, then you change basically the thickness of those double layers. So this is the Dubai thickness, here in high salt concentration, here low salt concentration. It changes the thickness of the double layer, and part of the stiffness of a gel is related to the thickness of those double layers, and not just to strain. Even if you constrain the gel and disallow it to swell, you get a change in stiffness. And we did actually experiments. Here, this is a gel enclosed from all sides within a torsional testing bench, and enclosed within a ring, so that it cannot swell or shrink, but we can change the salt concentration in the bath. And then you find changing stiffness depending on the salt concentration. These are 3 different salt concentrations, 0.03 molar, 0.1 molar, 1 molar. As you change the salt concentration, even at constant strain, you still get a different stiffness. And this kind of result has been found by us for gels, but by Alan Grodzinski in MIT for cartilage. Here we have a dependence of stiffness on salt concentration as such. And you see here shear modulus plotted versus ionic strength, and you see quite significant changes in stiffness. all of these, we can plot, build this into the model so as to represent really what is happening in such a gel. And automatically, when you assume these shear modulus to depend on salt concentration, also electric potential depends on strain, which may be extremely relevant to mechanotransduction as well. Now, a second theme I would like to talk to you about is fracture. And fracture is a phenomenon which is extremely relevant to disc degeneration, because most of disc degeneration is associated with fracture. And fracture means that very locally at crack tips, there are very large strains, even in relatively stiffer environments such as disc or cartilage. And the strains are large, and there also we expect local mass balance violation. Now, the disc is known to be cracking or tearing as it degenerates, and usually this tearing is not very much associated with loading. It's actually intrinsically associated with aging, swelling, loss of fixed charge density because of the degeneration. And so this fracture is, on one hand, relevant to biology. On the other hand, finding also funding for this kind of simulation on fracture using coupled to swelling is a difficult one. Now, I showed you in the beginning the gel from the diapers, and you see also there was fracture. So we got actually funding through Procter & Gamble to do this kind of simulation, and we started on fracture propagation in swelling media. And I will start with an experiment. An experiment relates to a gel, and the nice thing about gel, you can look inside it, which almost you never can do in a solid, but here you can look inside it, and we have the gel, a piece of gel with a small crack initiated in it, fixed to both sides to a drawing bench, the grips of both sides of the drawing bench, and you're going to move apart one side compared to the other and observe the cracking inside the hydrogel as it propagates. And so this is the gel. You see the initiating crack here, and we're moving apart the jaws, and you see that it progressively propagates. And we hope it to be a one-dimensional phenomenon, but you see how it is a very complex thing happening at the crack tip, and you should think that similar things happening in the disc and to cartilage. But if you look very carefully, you will see that it doesn't propagate in a continuous fashion, but much more in a stepwise fashion. Suddenly it propagates, then stops, it propagates, it stops. And we find this even for just strictly homogeneous material. So gel is homogeneous. There is nothing like inhomogeneity. And if you look at the surface, you find that there are actually teeth along it, which also indicates that it is stepwise progression. And so we also could show that the distance between the teeth depend on the Young's modulus. You did many of these experiments, and you see that Young's modulus, as Young's modulus increases, you get a longer distance that it propagates each time between the steps. And the time it pauses does the opposite. It is higher for low Young's modulus and lower for high Young's modulus. So interesting finding, but we tried it also to simulate this. And you say, well, we use XFEM. XFEM is an advanced method of finite elements, well known to do fracture propagation. And people in concrete and in steel, etc., they use it. But we wanted to use it for poromechanics. And so this is a crack inside a poromechanical medium. And the XFEM, nice thing about XFEM, you don't need to do remeshing. You just do enriching of nodes. as you propagate through the mesh, you actually progressively enrich nodes as you go through the finite element analysis. And so you get at some point a whole path followed by the finite element method and progressive enrichment of all the nodes which are tainted in black here. And what you basically do is using the same thing as regular finite elements, using displacement degrees of freedom and pressure degrees of freedom, but you enrich the displacement and you enrich the pressure by means of an extra discontinuous shape function. And this is very standard stuff, only what we did along the crack, we had pressure defined inside the crack, but also a pressure defined on the left side of the crack and on the right side of the crack. We had 3 pressures in each point, because the thing is that we expect these 3 pressures to be systematically different inside gels. And so we allow fluid to flow from the crack into the formation, into the gel, and from within the gel, it is flowing as well because it's porous media, and also within the crack it is flowing. So these 3 things are accounted for, and also there we got funding from again another source, and hydraulic fracturing is a very important thing in oil industry, and so also there we use fracture. And this is a simulation of a fracture propagating inside a porous medium. And you can actually show that under gravity, this fracture propagates, but typically it's going to propagate horizontally, even if you start vertically. And I can show you more simulations. This is a small initiated crack, initial crack. We introduce some fluid pressure inside, and then it propagates progressively, goes into existing cracks which are already into the structure, and then you get exchange of fluid between the new crack and the existing crack, and so progressively you get propagation of fracture. And also here we tried 3D, and we can show that 3D also something is possible, but also there the stability may be disappointing. Now, we go back to our experiment. Our experiment is a hydrogel with an initiated crack, and we simulate in finite deformation this time the propagation of the crack inside the gel, and we can plot displacement or pressure, and we have a propagation of a crack which is definitely, as you can see, in the range of large deformations. And what we find is spontaneously that our system predicts stepwise propagation. It predicts stepwise propagation. It does not propagate continuously, but stepwise, despite the fact that the material is strictly homogeneous. And we find also that propagation length between the different teeth is increasing with shear modulus, which is consistent with experiment, and also the pause time is decreasing with increasing stiffness. So also there we find consistency, at least qualitatively, what's happening inside the gel. Now the question, why is it staccato? What happens is in poromechanics things are kind of more complicated. In a solid, you have crack. Ahead of the crack, what happens is that there is the material is somehow torn apart. It needs to be torn apart because that is going to allow the crack to propagate. So you get a triaxial tensile state ahead of the crack. And this happens in poromechanics also, only it is the fluid which is under pressure. And this under pressure attracts fluid, and the fluid goes towards that point, and then progressively the fluid pressure goes up again. And what happens is that this tensile load is transferred to the solid, and then you get propagation. And again, you have the same thing happening again. first the fluid taking up the tensile stress, and then progressively handing it over to the solid. And it's in this way, we think that we can understand what is happening inside this gel as it is propagating. So we have fluid flow towards this center, and progressively we see that the effective stress is increasing. Now, what you can show in gels is that typically the propagation distance squared divided by the pause time is in the order of magnitude of the pressure diffusion coefficient. What is the pressure diffusion coefficient? It is the hydraulic permeability times the stiffness. And you find, therefore, that you can assume that this stepwise propagation is directly associated with fluid flow inside our gel. Now we can do also simulation of several cracks at the same time in finite deformation, and you see them propagating and going inside, as you would expect it to happen in a gel, but also as you would expect it to happen in an intervertebral disc. And we can actually show also that without loading from outside, a gel can start cracking. And this is what happens in the disc. In the disc, you get crack propagation, and you can show that different people with having very heavy loaded spines and other which have low loaded spine, whatever happens, it's always so that cracks develop inside the disc. And this shows actually a simple experiment. This is a cylinder of a gel, but which has been cross-linked, so it cannot stand swelling very well, so it goes in a crack. And this is actually in another view of the same sample, but produced by a mirror. So here you get the swelling, and what happens, it cracks into pieces. So the opposite you can do as well. You can actually deswell the gel, and it goes into pieces as well because it cannot stand this kind of cracks. So this is kind of idea that we can create to understand what is hydraulic, what is disc degeneration with time using this phenomenon. But also there we are using on one hand the intervertebral disc application, on the other hand also oil field applications, where also there it is known that shales, which are also swelling, can actually cause a lot of trouble to oil companies as they are drilling into the soil. Now, a completely different applications, which we are seriously working on, and also using mixed hybrid finite elements, using Raviart-Thomas elements, is a application in the science of in the world of cardiology. In the world of cardiology, there is a lot to do about simulation in 3D of the electrophysiology and the contraction of the heart. But if you think very carefully, damage of heart, failure of heart, is in 95% of the cases associated with fluid flow. Fluid flow, coronary flow inside the heart being disrupted for some reason, and somehow the heart, the blood flow cannot reach certain areas of the heart. And so we want actually to integrate this complex flow phenomenon inside the heart using standard methods from poromechanics in order to simulate this during contraction. This is here the system of coronary flow with the left descending coronary artery, the circumflex coronary artery, and the right coronary artery, all feeding the heart from the aorta, which you see here on top. Now, What we can do is, Eindhoven has a very advanced model to simulate in 3D contraction of the heart coupled to electrophysiology. And we take that model, and we have also an axisymmetric model of a heart, left ventricle. And we take that model and we add to it a coronary circulation model in which we distinguish between arteries, arterioles, capillaries, venules, and veins. And we simulate blood pressure, blood flow during contraction. This is during end diastole and ejection. We are working on having simulation of blood perfusion inside a beating heart, so that we can do prediction as far as the effect of specific cardiac devices on this phenomenon. Here, this is a view of different compartments inside the left ventricle: arteries, arterioles, capillaries, venules, veins, and we can simulate this as a function of time. This is done specifically here for end diastole, but we can take different times during contraction to simulate this coronary blood pressure and coronary flow in order to predict failure of the heart. This is ongoing work, and as a conclusion, I would like to tell you that mixed hybrid finite elements has added value compared to normal UP formulation as available in Abacus, for poromechanics, particularly for very large deformations, but also for non-homogeneous media. At low stiffness and high swelling propensity, gels exhibit surface instability. Shear modulus of gels depend both on strain and ionic concentration. There is evidence of staccato crack propagation in homogeneous gels, and the XFAM method that we developed is able to predict the staccato for propagation of gels of cracks in gels. Multiple cracks, merging of cracks, bifurcation of cracks are within reach of XFAM simulation, and coronary circulation modeling in contracting heart may lead to virtual environment, which allows us to simulate cardiac devices before launching into animal experiments and clinical trials. So I have to acknowledge many people who have contributed to this work, and also many companies who had helped in financing all of this. So maybe there are many questions.
Wow. Wow. Thank you very much, Jacques, for this amazing talk today. So we have time for questions. I hope that.
Okay.
Thank you very much for the talk. I would like to ask about this change in the same shape functions that you mentioned. Do you also apply it in the displacement degrees of freedom or only in the fluid flux or pressure?
You should think, if you think for solids, you write down classical equations of solid deformation using displacement as degree of freedom, automatically complies with local mass balance. Why? Because you make a mesh and there are no gaps between the elements. The elements stick to each other very nicely, even if they continue they continue deforming, they stick onto each other. So the mass balance is automatically accounted for a solid. What is not accounted for perfectly is the momentum balance. Momentum balance is accounted for on the average. So there you are not perfect. For the mass balance, you are perfect in a solid. And when you add fluid, you do solid-fluid simulation, you comply with mass balance for the solids perfectly, and your solid, your momentum balance is going to be accounted for on the average. But for the fluid, you did the opposite. because your pressure is continuous. There are no gaps in the pressure. It's not that one side of an element has another pressure than the other side. But you have problems with mass balance. And the reason for doing this thing of Raviart-Thomas element is to account for mass balance locally for the fluid. And the reason why we get better results is because we account for this mass balance. And it's an old trick which is used in standard way since many years in fluid mechanics. So all the computational fluid mechanics packages account for that. But in poromechanics, people never minded about that. And so when you account for that, you have a much better model, a much more stable model. And the computational time is same. It's not that we are doing something much more complex, because we just have the displacement and then some, here, Lagrange multipliers, but it's basically pressure or chemical potential. It's same thing. In size, it's not more complex, only it's a little bit more complex in programming. And we've been pushing the abacus to build it into their standard package. They promised us to do so, but I haven't seen anything happening yet. Usually you should think if you give them the equations, you know, they solve it in 2 days' time. One employee from them can have it inside abacus. So it's not that it's a lot of work, because it's extremely routine in putting new elements into abacus. But you know, it's business, and as long as it's not clear to them they really need it, then it doesn't happen. Now there is one thing, you know, developing finite elements, the thing you need is to have companies behind you, because we are customers of abacus, but they give us abacus almost for free, because we are educational and etc. And we don't have money, etc. So we get it almost for free. Now, if you go to Procter & Gamble or Shell or whatever kind of big companies, they pay, I think, maybe 400, 500,000 euro per year for their subscription to abacus. And what they have people walking around in their research labs paid by abacus. And they're just helping people. So what you need in order to get this kind of developments into commercial packages is have the support from these big customers. Because abacus worries about having Procter & Gamble as a customer, but they don't mind about University of Eindhoven, or it's of no value to them. So you need to have support from them. And one of the issues that we have when we really move towards biological application is that we need to have support from a multinational to support this. This whole thing of blood perfusion, getting into a commercial package is one thing, but the other thing is getting it supported by the company. And you get it supported by the company only when there is a significant market for them. And you have to justify that this market is big enough. Now, Abacus has started a project on living heart. And what happened is that one of the guys from Abacus, he was manager there, and he got a daughter. And this daughter had a congenital heart disease. And then he was watching on the pediatric cardiologist studying the MRI of his daughter and looking what he's going to do. And he was flabbergasted that this guy was going to cut into the body of his small baby daughter without doing any computation whatsoever. He just started cutting. Now, if you think about what we do, I came here by flight. Now, this plane, with which I came here and which many others used, we are pretty sure that when we leave from Holland, we're going to arrive in Barcelona without much trouble. Why? Because every small part of a plane is calculated by means of finite elements, on fracture, on failure. Every small piece is calculated everywhere. And therefore, we know for pretty sure that we are going to arrive safely into Barcelona. Now, it is incredible that when you start working on a heart, that you have no computational tool whatsoever. One works on feeling, starts cutting and reconnecting and things, no computation whatsoever. For failure of heart, there is no computational tool, nothing. Because it's disruption of blood perfusion, and nobody does blood perfusion in finite elements. People are used to do stresses and strains. So people are doing stresses and strains because they're used to stresses and strains. But a cardiologist doesn't know about stress and strain. He wouldn't even know the difference between stress and strain. So while he knows everything about blood perfusion, and the finite element people don't know about blood perfusion. I talked about blood perfusion with the living heart people from Abacus. They never heard about it. They don't realize it exists. They just do stresses and strain in the heart. So there is really a problem of communication between, on one hand, cardiology, and the other hand, the engineers. And they talk simply a different language. They do different things. And that's why there is a real serious issue, while the reality is that there are 18 million deaths a year on cardiovascular disease. So there is a lot to do about it, much more than those planes, because those planes, you know, there are many planes in the air, but there may be 1,000 deaths a year, a few planes falling down every year, something like that. Now you can say that's very bad, okay. But 18 million is much worse. So there is an urgent need for finite element analysis and comparison with experiments, prediction of what is going to happen, and it's very difficult to get it going. It's really a challenge. And so we are working on it. We think that it's possible to do it. And I really believe that if we continue working on it, we're going to convince the people. But how many years it will take, I don't know.
Thank you.
I think just a comment, that's just amazing what you've said about this blood perfusion stuff. A few weeks ago, I was having a beer with a friend of mine. She's a vascular surgeon at the hospital clinic here in Barcelona.
Yes.
And she said exactly the same thing. Say, what we are lacking are model computations for blood perfusion in order to improve our interventions. So I was really basically struck by what you've said.
Yes, yes.
Such convergence.
Yes.
Terence.
Thanks very much for that. Just along the same lines then of blood perfusion, but going back to the disc, and I'm just wondering if you have any thoughts in relation to modic changes and the subchondral bone and the effects of the hypertension in that area and the pressure of blood perfusion in that area, and whether that can have any link or mechanical effects in terms of vertebral end plate disruption or end plate defects.
I think if you think of pressure in the heart and in arteries, you're thinking about a few kilopascal. Now, if you think of pressure inside the disc, you're talking of much higher pressure. You're thinking of many megapascal. So the order of magnitude is much different. So if you think of what is happening at the end plate, the osmotic pre-stressing and the loading on the disc is probably much more important than the pressure into the arteries. Now, what definitely can play a role is what is happening on the level of capillaries. And I think there are also huge gaps on what is exactly happening on the level of the microcirculation. I realize that microcirculation just physiologically is very poorly understood. And it is extremely important, not only in disc degeneration, but also for diabetes. Many issues with cardiac function and also brain is associated with microcirculation, and usually neglected for the simple reason that if you look at X-rays, you see large arteries. You can see stenosis, occlusion. Immediately you can say, well, I'm going to put a stent and problem is solved. Now the reality is that a large part of the patients don't have any stenosis or occlusion and still have problems with heart or brain function. And you cannot find any lesion, and especially ladies who complain about heart problems, they don't have lesions, not observable lesions. But on the level of microcirculation, a lot is happening, which we never see. And the cardiologists and the spine surgeons and the brain surgeons don't see what is actually happening. And there is a huge gap, I think. Even simply of physiologically understanding what is happening. One of the things we are researching now is, and that we do with microfluidics, we are trying to understand the following phenomenon. It is known that there is something like Farus-Lindquist effect, namely that the red blood cells are always flowing a little bit faster than the plasma. It's a little bit faster, maybe 10, 20, 30, 40%. And the difference becomes more as you go to smaller blood vessels. Now, in capillaries, you find that during exercise, the flow in the capillaries is for red blood cells, maybe 30, 40% faster than plasma. But if you look at a resting muscle, for some mysterious reason, suddenly this ratio becomes completely different. The red blood cells are going 3 to 4 times, 5 times faster than the plasma. And nobody understands why. This is not just convection. It's just something special happening there. And we are trying to illustrate this on microfluidics. But this is just a very simple phenomenon which is observed everywhere in microcirculation, and it's not understood. So there are things which need to be researched on that level, and I think there is a very great need from the clinical point of view, because cardiologists don't know what to do. And I think for disc, it may be a similar issue. What's happening exactly at the interface between the cartilaginous end plate and the vertebra is, I think, extremely important. That's one thing, and probably poorly understood, because we don't know what's exactly happening. So
yeah, thanks very much.
Yes. Yeah.
Yes. I have, well, thank you for the talk. I have a question related to the fracture simulations. Do you think that could be possible to include in these fracture simulations hydrogels containing cells and kind of predict how these fractures can happen with cells inside the hydrogels?
Oh, putting cells inside the hydrogels.
As a 3D culture model, for example.
Yes. I think it would be worthwhile doing, because I would be pretty confident that you can measure that cells sense the fracture. If you would kind of doing something with immunohistochemistry or whatever, showing what is happening with cells directly at the crack tip, I'm pretty sure that you will find that the cells are intelligent enough to know there is some fracture there. And how it happens, I don't know. But we are suspecting from our side, and I'm closely cooperating with someone on this subject, is that we are suspecting that piezoelectricity may be an important way. Streaming potential and diffusion potential and Donon potential may be important as well. But quite often, piezoelectricity is put aside because they say, oh yes, that's too small, etc. We have the feeling that it might not be, that it might be actually one of the methods through which the cells at a distance know that there is something happening and something has to happen, and that upregulating takes place thanks to the fact that they know, oh, there is a fracture there, or there is some inflammation there, or whatever. And of all of the mechanotransduction that we know, I think we know a lot, but I think we don't know everything. And one of the pathways we are testing is the voltage-gated ion channels and electrical phenomena. Because electrical mechanical is so intimately linked in the extracellular matrix that we think that this line of study should be explored. We can show that we've shown in DISC that voltage-gated ion channel responds to load. That definitely, without any doubt, we have clear evidence that voltage-gated ion channels respond to load. The pathway through which it happens is still unclear. But I think it is worthwhile doing. The trouble you may have is that you cannot exactly predict where the crack is going to go. But if you have a controlled experiment, yes, you could do it. Good idea.
Thank you.
Okay.
Okay, thank you very much, Jacques, and all of you. With this, we close this session of the morning. And let's go eat.
Now that you know the campus,